morphologically rich language or a free word order language, which is the case with quite a lot of languages. So let's see. Yeah. So Sanskrit is a classical language with about 30 million extant documents, and the number is much bigger even if you combine other classical languages like Latin or Greek. Uh, so Sanskrit has been influenced by fairly advanced disciplines of prosody, phonetics, and grammar, which has been existent since 2500 BC. And several of the characteristics expressed by Sanskrit happens to be of not of much consequence to languages that are focused by mainstream NLP. Hence, those are not really addressed. So when I talk about characteristics of the language, it's not just constrained to the linguistic aspects. Some of them are constrained by the usage of the language. So Sanskrit is a relatively free word order language. It has rich morphology, rich compounding, and the words often perform sandhi, that is, the words undergo phonetic transformations at their boundaries, thereby often obscuring the boundaries of the words. Moreover, the language, we have existent texts for that spans about 3 millennia, and hence the linguistic style has often varied, the syntax, even syntax has often varied across this time span. Most importantly, there was a rich oral tradition prevalent, and because of that, a lot of the texts are written in verse format. So this results in a completely different set of requirements for processing these texts. Sanskrit is a low resource language, hence we have limitations with lack of task-specific training data. We don't have a lot of tools available. So just to give an estimate, it would be very difficult to scramble 1 million unlabeled monolingual sentences for Sanskrit. So that's the level of low resourceness we are talking about here. So we often don't have enough training data for several of the tasks, but I'm talking about just unlabeled data itself is quite scarce. So Sanskrit expresses high lexical productivity. So if you think German has long compound words, then you could consider Sanskrit as German on steroids. So, and compound segmentation becomes crucial even for low-level tasks such as morphological parsing or syntactic parsing. So the sequence that you could see here is actually a single word that contains 9 lexical items. This is basically an exocentric compound that describes a particular person. So given that it is coming from a literary work, this is a bit more descriptive than what we are normally familiar with. So this compound is basically, it's Pravara Muguda Mani Mariji Manjari Chaya Charchada Charana Yugala is basically a 9 lexeme compound. And often it will be difficult for us to process these words unless we know what are the lexical boundaries here. Sanskrit is again a free word order language, and here I have taken the liberty to cut off the relatively part. So typically when I mention this, that Sanskrit is a free word order language, people often come back and ask, like, how free can that be? So here is one example. So if you see here, this sentence, the sentence summarily can be said as, there is a person Valmiki who is the subject here. The person is asking something to another person, Narada. So the words of importance here are Narada, Valmiki, and Pariprapacha, which means ask. So if you see here, the object comes before the verb, and the verb comes before the subject. And more importantly, the object and the verb is appearing in between the adjective of the subject and the subject. So Tabaswi is a word that is the adjective to the subject Valmiki, and you could see that the object and subject is appearing before it. So this is the level of free word orderness that you could find in a language like Sanskrit. So naturally, why this happens? So one thing is that, yes, Sanskrit has a rich morphology, and that enables freedom in word ordering. The morphological markers encode the structural information. So in this case, I could see that, or we could a person fluent with Sanskrit could infer that Naratam is in accusative case, hence it has to be in the object, and Valmiki is in the nominative case, hence it's highly likely to be the subject. Um, so, of course, the rich morphology enables the freedom in word ordering, but still this doesn't answer the question that why should someone make such a random ordering of the words? Rich morphology is displayed by a lot of languages. For example, Czech has very similar fusional structure like Sanskrit, but you probably won't find such a mixed order in Czech. So one of the reasons here is that Sanskrit had a rich oral tradition. And due to this, there has been an influence of prosody in Sanskrit constructions. So it so happens that the prosody in Sanskrit prescribes 300 odd metrical patterns, and the verses has to adhere to one of these patterns. And metrical patterns are nothing but syllable level binary patterns. So when a poet writes a poem or a verse, the poet is constrained to follow this metrical pattern, and based on the length, the possible cases are even lesser. Um, so here, the poet exploits the free word orderness to adhere to the meter constraints. And in this process, the verbal cognition takes a backseat. Sanskrit sentences also express sandhi. Sandhi is nothing but the euphonic assimilation of sound at or across word boundaries. So these are basically phonetic transformations due to modification and fusion of sounds. This is very similar to what we observe in connected speech, like wana or gotcha, which we could find in English. However, the difference here is that this connected speech is faithfully preserved in writing, and this happens at a much larger scale in Sanskrit. Yeah, for example, if we consider the sequence Gurva Lambana, here it is a sandhi of two possible words where the first word is Guru and the second is Alambana. So the O in Guru gets converted into Va when we perform sandhi. Similarly, in the case of Vidyapyate, there are two A. The A with a bar is basically the long A. So they merge together to form single A. The third and fourth case that you see here is a very specific case where you could find that basically, if you see here, one of the possible split for Kurvan Apnodi is Kurvan Na Apnodi, and the other one is Kurvan Apnodi. So the word Na here means negation. So sometimes it's possible that you might completely miss this part of negation because both are legally valid, or like both are linguistically valid splits for the sequence Kurvan Apnodi. I mean, the one you see here. But Sandhi modifies the constructions only at the phonetic level. It does not alter the meaning of the words. So Sandhi is different from compounding. This is merely a phonetic level transformation. The generation is unambiguous, but the analysis is not, as we could observe from the third and fourth case. So these are the tasks that we consider for this framework. So basically, we consider 4 morphosyntactic tasks and 1 prosody level task. In addition to that, we try 4 different combination of joint formulation of these tasks. So as per the hierarchy, we could see that we perform joint word segmentation, morphological parsing, and dependency parsing. We also perform joint syntactic linearisation with morphological parsing and word segmentation. So we at the end, we end up doing 4 joint tasks and 5 independent tasks. And for this, we propose a generic framework for multiple structured prediction tasks. And this is a framework that uses energy-based models for solving multiple structured prediction tasks. Ours is a search-based structured prediction model. It is a graph-based parsing approach that makes use of artifacted approaches. The highlight here is that we automatically learn our feature function, and we make use of a sequence level margin-based loss. So in this work, we have achieved either state of the art in all the tasks, or we are the first to introduce those tasks. Our feature function is common and it is agnostic to specific tasks. And one of the major advantage here is that owing to our input representation, we have extremely low requirements of task-specific training data as compared to the neural counterparts. So our structure prediction framework consists of three separate components. There is a graph generator, there is an edge vector generator, and our structure prediction model. So the graph generator takes a user given sequence, it converts it into a graph. The edge vector generators take this graph and produces vectors for feature vectors for each of the edges. And the graph and the edge vectors form the input to the structure prediction model. Once we have that, this arc-factored model basically learns a function to score the edges of the graph. And our inference basically searches for an induced subgraph from the input graph. And this inference is predetermined, but it is determined based on the task at hand. We use sequence level margin loss for this. And one important aspect here is that once we convert a sequence into the graph, we do not use the sequence information that is available at the input. And so basically our input is a graph, and hence we stick to EBMs for this very specific reason that they enable non-probabilistic training of structured models. And this avoids the need to normalize over our output space, which is the case with CRF. So the easiest way to think about this model is in terms of the first order graph-based parser by McDonald et al., published back in 2005. So in this case, in our model, if we are doing dependency parsing, yes, it is very similar to the McDonald et al.'s model, where we are given with a sequence, we convert it into a complete graph. This graph is an unlabeled graph, and we obtain the edge vectors for each edge in the complete graph, and then we pass it to the energy-based model, which predicts a minimum energy spanning tree using the Edmond-Liu algorithm. And so in summary, this model is basically, it consists of a graph generator where we use Sanskrit heritage reader, which is a lexicon-driven shallow parser. And it enumerates all possible word splits, compound splits, and morphological analysis. And the size of the search space is constrained by the graph generator. Our edge vector is a typed language model with morphological constraints. The constraints are automatically learned, and we have a feature function with 850 features, each of these automatically learned. Each feature is a morphological constraint, and it is common for all the tasks. So here, one thing that I need to stress here is that, so if you look into the learning model, these are well-known approaches in structure prediction for the past 10 to 15 years. So what makes our model effective is our graph generator and the edge vector generator. So it enables us to achieve high performance, and we don't have to design our feature space manually, or we don't have to use handcrafted features. We can automate the feature learning. So we might not have seen in our previous example, we might not have observed like where exactly does this graph generator come into picture. So to elaborate that, let me give a little bit more information here. So when we think of a dependency parsing task, we take a sequence of tokens, but we assume that for each token, we have the surface form, stem, and morphological tag information available in the goal data, and we use that for training. However, this assumption is not realistic. We often only have the sequence of tokens with us. So in such cases, we have to perform both morphological parsing and syntactic parsing to get this task done. However, the problem with Sanskrit is that tokens show high degree of syncretism and homonymy. So Sanskrit is a morphologically rich fusional language with 1300 possible morphological tags in the tag set. So let us consider a token sequence here, Shriya Padihi Pashyadi. So there are three words, three tokens here. However, if we perform the analysis, morphological analysis for these three tokens, we end up with 8 different analyses. 5 for the token Shriyaha, which varies in the morphological tags. 2 for the word Pashyati, which has, again, 2 different morphological tags. So what we do is that we take each analysis and represent it as a node, And this information is obtained from the lexicon-driven shallow parser that I mentioned previously, or our graph generator. The so the input sequence is converted into a graph, and we completely ignore the sequential information. It doesn't matter whether Shriha appeared before Pashyati or after Pashyati. And each analysis of a token is a node. Once we have that, we form a really dense graph here, where we form edges between every pair of nodes which are not conflicting. So here, by conflicting nodes, what I mean here is that if there are two nodes that are presented as alternatives to each other, or in other words, if there are two nodes that cannot coexist in a final solution, then we call them conflicting nodes. So in this case, two analysis of Shriyaha, the one with a feminine plural accusative and the feminine plural nominative, they cannot co-occur in a single sentence because they are suggested as alternatives. Hence, there will not be edges between them, but there will be an edge from every other node which are not conflicting. So now for this task where we have to jointly perform morphological parsing and dependency parsing, the idea is that we have to search for a subset of nodes from the given set of solutions. So if we have to perform dependency parsing, our inference is a spanning tree. If it is morphological parsing, we search for a maximal click. If it is joint morphosyntactic parsing, we search for a Steiner tree. A Steiner tree is a maximal spanning tree with minimum energy. That's what we will search for in this task. So as you can see, from an 8-node graph, we get a final solution, which is a 3-node graph. So yeah, so in the case of joint morphosyntactic parsing, this would be how the model work, or this the basic flowchart. Yeah. Now there are cases where it is often the case that we may not have segmented sentences that are available for us. So it is possible that one or more tokens may be fused together. This does not change the syntax or semantics, but things change phonetically. So we need to perform word segmentation as well. So, and we can again extend this model to perform joint word segmentation and morphosyntactic parsing. So if you consider this sequence where you have a sequence of 13 characters, Satyam Apriyam, it could be segmented into either Satyam Apriyam, or it could be segmented into Sati Amapriyam or Sadi Amapriyam. So if you observe here, there are characters that were not originally present in the input sequence. So this happens due to Sandhi. Due to Sandhi, you could find characters which were not originally present. Further, each such segmentation can have a morphological analysis of its own. So we will have a much bigger graph than the original number of analysis. And these both information are provided by the lexicon-driven shallow parser. So we use this information. We generate the edges, and we pass it to the energy-based model. And for word segmentation, we again use maximal click as our inference. So now I will probably go into much detail into each of these tasks that we are addressing in this framework. So word segmentation is the task where we identify the words from a given character sequence. And so if you consider this 13-word sequence, there are 7 cases of such fused words. And of these 7, 6 of the 7 cases result in phonetic transformations. So what you see here in orange are the changes that happens due to Sandhi. So here there is Ramopi, which gets segmented into Ramaha Abhi. Similarly, Paramodara Sumukhaha, which gets converted into Paramodaraha Sumukhaha. Piduradeshat gets converted into Piduhu Adeshat. Further, we also do segmentation of the compounds or the compound splits. So here, Paramodaraha is a compound word with 2 components. And when we split this lexically, again, Parama is a lexeme and Udaraha is a inflection. So Sanskrit compounds have the final word with the inflection. So Udaraha is the inflected form and Parama is the lemma. So we pass this sentence into Sanskrit Heritage Reader. It provides us with all possible analysis in terms of Sandhi and morphological analysis. So with this, as our graph generator, our task is to find the semantically most valid exhaustive segmentation amongst the candidate solutions. And when I say an exhaustive segmentation, it is defined as a segmented solution that spans the entire input sequence. So this was kept as a means to just say that we should not give a partial solution. So given this is the analysis for the sequence, after we perform the segmentation, we should ideally get this segmented sequence. As previously mentioned, the morphological parsing involves identifying the morphological tag and the lemma for each of these inflections. And we could observe that in Sanskrit, there is high synonymy and uh, uh, homonymy. So if you look into the case yashaha, yashaha is a case of syncretism here, where there are two possible uh, analysis, morphological analysis for the word. Pituhu is a case of both homonymy and syncretism, because Pituhu has two possible stems, Pitru or Pitu, and Pitru itself has two possible morphological analysis. So altogether, we are considering around 1296 possible tags in our tag set. The real tag set might be much higher, but yeah, for this task, we assume the tag set contains only 1296 unique tags. Dependency parsing. So in dependency parsing, keep we keep or we stick to using the traditional tag set or a tag set based on the traditional theory, and this is called as Karaga theory, which was proposed again 1200 some 2500 years back. So we use about 22 tags which are mostly of syntactic nature out of the 45 syntactic semantic tags that was traditionally defined. So by using this tag set, the one good thing is that we could see that the syntactic relations rely heavily on the case markers of the nominals and the valency of the verb. And this can be put to use in effectively in our task. So what I'm trying to say here is that, so if we know that a particular nominal is in ablative case, then so you could see the case of a nominal in the y-axis. So there are 8 possible cases for a nominal. Then the number of possible relations it can obtain are just 2 if we assume that this word is having a relation with the verb. So, so this considerably reduces the label space when we have to do the prediction. We also perform the task of syntactic linearization. So, so we have previously mentioned that in Sanskrit, there are a lot of verses where the word order are often not uh, given. I mean, the word order is done in such a way to adhere to the metrical constraints. So the verbal cognition or efficiency of how much a speaker understands or how easily a speaker understands is often not taken into consideration. However, for pedagogical reasons, commentators often reorder the words in a verse and place them in the most easily understandable prose order. And in prose order, the Sanskrit sentences tend to follow subject, object, verb formulations. Indian languages in general tend to follow verb ending sentences, and most of them follow, or a good number of them follow subject, object, verb ordering. So here, the syntactic linearization task is to predict the anvaya or the prose order for a given verse sentence. However, verse information really doesn't help in the linearization process. So we convert this verse information into a bag of words, and then we try to get a proper order or a prose order from the bag of words. So again, the dependency analysis of a sentence doesn't vary as per the ordering. The dependency analysis remains the same. However, if we do the dependency analysis of the anvaya, that is the prose order, we find that the sentence or the projectivity is basically, it follows a weak non-projectivity. But there is no such guarantee for a verse. You could find all sorts of crossing of edges, but that is not the case with a prose order. The final task we address here is prosodification. The task is to convert a bag of word input into a sequence such that the generated sequence adheres to one of the prescribed meters in Sanskrit prosody. So meter identification basically involve that you take a sequence and you perform syllable level segmentation. Then we have to identify the weight of the syllable, which can be light or heavy. We call it Lego or Guru in Sanskrit. And a meter is a specific binary pattern. So, so if you see here, there is a case that, so this is the original sequence or the sequence which is already in the verse form. And this is the segmented sequence. So depending on the sandhi, operation of sandhi, the meter of certain syllables change. So when we write it in the fused form, Ramopi, where mo is a heavy syllable, but the moment we segment it, it becomes maha and a, both of them are light syllables. And sometimes if you see here, so there is this Pidiradeshat. So you could see DE here, DE and DRA here. So this is segmented into T hyphen RA. So the DRA is converted into T hyphen RA. So here what I'm just trying to show here is that this is actually a word boundary and a syllable doesn't really obey the word boundaries. You could combine characters from uh, different words to form a single syllable, as long as if they are, if they are aligned or if they are placed successively. And again, I am mixing up terms from phonetics or prosody and grammar. It's because in Sanskrit, we follow phonemic orthography. So there is a correspondence between the phonemes and the graphemes. So the task involves rearrangement of the words from a bag of words to, and then it also, we need to perform the sandhi, because if you look here, the original sequence belongs to one of the prescribed meters, which is Anushtub meter. However, we cannot say a valid meter for the segmented sequence. So that is why sometimes sandhi becomes essential when it comes to prosody level tasks. Yeah, so basically it's a two-step formation. Like you take a bag of words, first convert into a verse order, and then perform the sandhi at the relevant positions so that we can get a sequence that adheres to one of the prescribed meters. So are there any queries so far? Shall I proceed?
Yeah, it seems really interesting so far. Just, yeah, I'm happy.
Sure. Okay. So yeah, just to recap, our framework is a graph generator. It contains a graph generator, an edge vector generator, and a structure prediction model. And ours is an app factored model. Yeah. So this table summarizes the different tasks we perform and more importantly, the kind of inferences we use. So if it's for word segmentation or morphological parsing, we use a maximal click selection algorithm. For dependency parsing, we use the classic Liu-Edmonds algorithm. For the linearization tasks, both syntactic and prosodic, we use beam search. And yeah, for the joint tasks that involve dependency parsing, we use Prim's algorithm to obtain a Steiner tree. So yeah, these are the different configurations that we use for various tasks. We also add some linguistic constraints, some 120 odd constraints during our inference. So these constraints were applied during dependency parsing and linearization. And we do it both. We use this to prune the edges in the input graph. And we do it both before the inference and sometimes during the inference. So basically, we make use of the case information of the nominals to identify possible relations between word pairs. For dependency parsing, the constraints are applied to the search space such that we use principles of valency and also principles of expectancy. So expectancy might not be familiar with the traditional linguistic literature. So here what we mean is that valency is basically the relation between the verb and the nominals, but the expectancy is a relation between different words. It can be between nominal to nominal as well. In Sanskrit, it is called as akanksha. Uh, Similarly, for syntactic linearization, we use the principle of dependency locality, and this has been defined as sannidhi in Sanskrit, or proximity. So the learning and the inference methods are well-known approaches since 2005. the design of our feature function enables to make use of these simple approaches. And yeah, our feature function basically it automates the feature generation and filtering. So this is important from a point that for many morphologically rich languages, people still use handcrafted features to get state-of-the-art results in morphosyntactic parsing or even for dependency parsing, probably in the pre-UDFI era. So yeah, our features are morphological constraints defined over word pairs. We attempt to capture morphosyntactic constraints such as valency and expectancy. We use grammatical categories such as case, number, tense, etc. And this is important here because Sanskrit is a fusional language. So by fusional language, in a fusional language, a morphological tag is a combination of multiple grammatical categories. So we break down them into individual grammatical categories and use them as constraints. So the basic idea is that knowledge of case helps in identifying syntactic relations, and the knowledge of number and gender helps in identifying the agreement between the words. The feature values are from a typed language model. And this language model is also constructed based on co-occurrence of words and not based on the sequential information or on the n-grams. However, not all co-occurrences are useful. That's why we need to identify which of those co-occurrences are useful. And we basically obtain this by conditioning them on certain morphological constraints. And which are those morphological constraints? We again use path constraint random walks, which is a popular knowledge-based computation approach, to learn the useful morphological constraints. So we only define the literals along with constraints for forming the clauses. The clauses are, the relevant clauses are automatically filtered using path ranking algorithm, which comes with path constraint random walks. So just to illustrate this, how we construct our language model. So assume we have a corpus of just 2 sentences, or with one sentence with 3 tokens and another with 4. Then we basically represent each token with 3 types of information. We use the word, lemma, and the morphological tag information. So our language model is obtained from a morphologically tagged corpus, and the language model is represented as a graph or network. Here, the nodes are typed. So a node can either be a word or an inflected surface form. It can or it can be a lemma, or it can be morphological tags. So the edges are formed based on co-occurrence of nodes in a sentence, irrespective of the type of the nodes. So what I'm trying to say here is that, so if we have the word manasi in the second sentence, manasi here, and if you take its lemma manas, it will have edge to the inflection W4, that is balagasya, as well as satyam. It will also have edges to locative singular n, which is also a morphological tag. So irrespective of the type, as long as these nodes co-occur in a sentence, we will have an edge. However, we will not have edge between manasi and manas because they are not co-occurring here. So the edge between both the nodes have a, so this alone, this kind of co-occurrence alone can result in 9 different feature values for a given word pair. So once we construct the language model, we take an input sequence and assume this has only 2 words, balagaha and manasi. So if you see here, these 2 words don't co-occur in the sentence, in the language model. Sorry, what I meant to say was that these 2 tokens does not co-occur in a sentence in the language model. So we pass this information to the graph generator. Graph generator gives us the analysis for the words. And once we have this information, we are trying to create the co-occurrence information between manasi and balagaha, which is the word forms of both the nodes. We also try to create the information between manasi and bala, which is the inflection of manasi and the lemma of balagaha. And similarly, we can form 9 different co-occurrence information, and each of them can form a value in our feature vector. But we do not stop here. We extend the set of possible co-occurrences by conditioning them on morphological constraints. So the constraint can be a morphological tag, or it can be a grammatical category. So to represent this in terms of metapaths, again, quite a popular way to represent them in terms of heterogeneous information networks. So what happens here is that the L and L here show the lemma information of the input words. which forms the external nodes. The internal node can either be a morphological tag or a morphological category or a grammatical category. And this information is used to form different possible features. So we have 9 possible external node pairs and we have 540 possible constraints. So this would result in 4,500 possible features if we use only one constraint in a feature. But it, it exponentially blows up, and we can get more than 800,000 possible features if we use up to 2 constraints in a feature. And the co-occurrence value is calculated in a very simple manner. Basically, we take the count of co-occurrence of both the nodes in the language model, and we divide it by the count of the source node. So if we want to extend this in terms of a path or in terms of multiple constraints, what we do is that we simply take the product of this co-occurrence information. So if you have to see how can I reach from VG to VH, what we are trying to do here is that we are trying to find the co-occurrence information between VK given VG and then VH given VK. So it's basically we are computing the path score. So we use these feature templates to get our feature vector. So currently our model uses about 850 such features. And how do we identify these features from our set of different possible feature templates is using 2 approaches. We first used path ranking algorithm, and then we extended it and used forward stage path generation approach. So here, both the task, essentially what it tries to do is that it learns relevant horn clauses from a space of infinite possible clauses, where each path is considered as a restricted type of horn clause. We define the literals along with the constraints for forming the clauses. In PRA, the features need to be exhaustively enumerated first. So we only tried features with either 3 nodes or 4 nodes, but not more than that. But in FSPG, it basically uses a greedy data structure to keep track of the most viable or the most relevant features. So there is no arbitrary upper bound. So when we use PRA, we got something like 1,500 features, and when we used FSPG, we obtained about 850 different features. So FSPG uses least angle regression. So there is no need to arbitrarily stop or give a parameter to decide how many features need to be selected. But in the case of PRA, we basically use logistic regression to identify these features. Here is our dataset details. So if you could observe here, the training data are often like it's 8,000 or 10,000 or maximum of 12,000. So we have very limited set of training data here for each of these tasks. So for word segmentation, the final model that gains the most is the click EBMF. So it uses FSPG as the feature selection, and it uses maximal click as the inference. So we achieve the best results in terms of precision recall and F-score. One of our baselines, which is RCNSS. So this was a EMNLP 18 paper. It's basically a character level sequence tagger. So their model achieved better performance in terms of perfect match, like how often you get a perfect match at a sequence level. So this model, it uses about 500,000 sentences as against 8,200 sentences in our case for word segmentation. But yes, to be fair, we use a lot of linguistic information from the shallow parser, and then we use these vectors that encodes a lot of linguistic information. However, their model is generic and it doesn't encode any language specific information. For morphological parsing, we obtain somewhere around, our morphological parsing results are about 95.33 in F-score. So here, this is the factor CRF model, which achieves 80.26 in comparison. Yeah, so for syntactic linearization, we use again a beam search based inference, and we obtain a blow score of 59.38. And this is an improvement. There is a close to or more than 4 blow score improvement in comparison to Kavya Guru. Kavya Guru was the baseline we we built, which was published in ACL 19. So this one is a seek-to-seek model, which makes use of structured prediction losses. Similarly, BSO is the work from Weissman and Rush. It is the beam search optimization work. So yeah, in comparison to these models, our model performs much, there is a lot of improvement in these models. And the star here shows that our model, the models with beam EBMF and beam EBM star F, the differences here is that in beam EBM star F, we use linguistic constraints during inference. However, that is not the case in beam EBMF. For prosodic linearization, we find that again, our model performs much better as compared to BSO or Kavya Guru. Linear STM is again the work from Alexander Rush's group, where they basically use a language model for linearization. For dependency parsing, again, we tried with different combinations. So we tried the easy first parser. We also tried yet another parser from basically the Hebrew morphosyntactic parser, retrained for Sanskrit. Yeah, so again, our model performs much better in comparison to these models. However, if we go to the neural models, what we find is that the biophane parser or the DCST, which is also just a self-training variant of the biophane parser from Dorset and Manning. So these models perform comparatively incomparable performance actually. So yeah, I mean, we were able to get this performance close to again 85 for these neural models. But the difference is that, so our test data set contained about 1300 sentences, of which 1000 are from the same domain of the training data. So we use the test data split, that is the STBC, and our models are trained using the training data split of this corpus. And when we change the domain, so we use some 300 sentences from a different domain, we do not find much difference in the performance. We get very similar performance, in fact, slightly better also in this case. However, the same set of sentences when given in a different permutation. So the model was trained on prose. The test data for the out of domain was also in prose. The performance was comparable. But the moment we gave the same set of sentences, but in a different permutation of the input, the performance often drops to half. So it's the same set of 300 sentences presented in different permutations, leading to stark differences in the performance. But this is not the case with our model because we do not use the sequence information at any point. So irrespective of the permutation that we provide as input, our input graph will be the same. Yeah, so we could observe that, yeah, the joint, in the joint tasks also, so yeah, for the joint task, we basically compared with different combination of our models. So in the interest of time, probably I will skip this. This is the performance for different our different edge vector selection approaches or the feature vector generation approaches. And we can find that FSPG performs much better as compared to the other models. In the case of PRA-based approach, what we have done is that we used mutual information regression for our feature selection, and we used the co-occurrence information for the label information. And that model with only one extra constraint, this particular configuration yielded the best results. Yeah. So we also performed experiments on Czech. So we basically took the two shared tasks, the Cornell 2018 shared task for dependency parsing and the morphological analysis and lemmatization task for the Sigmorphon 2019 shared task. So what we can observe here is that for the Sigmorphon task, our model performs the second best, second only to probably Sarland 2. And for the Cornell 2018 shared task, our model performs the best in comparison to other models that was presented for the Cornell 2018 shared task. So yes, Udify obviously performs much better than this model in term for Czech, but yeah. We did an extension to this model where we take the case of joint morphological parsing and dependency parsing. So what we observed here is that if we perform joint morphosyntactic parsing, we do not need to show one token per analysis. Instead, we could convert it into a multi-graph, which makes it one node per token. And by doing this, we could use the exact inference algorithm that was used for dependency parsing. On top of it, we actually employed a non-greedy edge pruning approach, which was only possible if we convert it into this multi-graph formulation. And yeah, so we performed this and we found significant improvements to our model. Yeah. So you could again find the DCST or the BioFN were coming close with 84 or 84.36 UAS, but our model was somewhere around 87.46. For the joint morphosyntactic parsing task, we are getting a UAS of 83.16, which is, yeah, and LAS of 79.33. Now, yeah, there are some possible extensions because, yeah, these were the learning methods were quite trivial that we use here are quite simple in the sense. So actually, if you look at again at the hierarchy, the point is that syntactic linearisation and dependency parsing are two syntactic level tasks. So often one could teach the other. At least for the neural models, we have seen that how the performance varies based on the permutation of the input or the word order of the input. So one way we could formulate it is using dual decomposition, where we perform joint morphosyntactic parsing and joint morphological parsing and linearization. And we could just make sure that the nodes agree. The predicted nodes in both these tasks has to agree. That is one condition we could use it in dual decomposition. We are also exploring approaches to use by dual learning. Another area that we are interested in exploring is how we could formalize the morphological constraints into a logical formulation and probably use them in as a loss function or as a part of loss function. So the case and the syntactic relation, how can we make use of it? Currently, these are used as constraints during inference. So yeah, and how can we improve this permutation invariant performance for neural dependency parsers? Yeah, so in conclusion, yeah, our approach is a general graph-based parsing framework for Sanskrit. We use non-sequential processing of inputs, and yeah, we automate our feature generation approach, and we use less than 10% of training data as compared to several neural counterparts. Thank you.
Thank you very much, Amrith. I'm going to stop the recording there.